Hello there, and welcome to Science for Sleep. Tonight we're exploring one of the universe's most fundamental rules, why entropy always increases, and the real reason behind this cosmic truth that governs everything from your morning coffee cooling down to the eventual fate of all the stars. You might think of entropy as disorder, as things falling apart, but there's something much more beautiful and precise happening here. It's about probability, about the countless ways energy can arrange itself, and why the universe tends to drift towards certain states rather than others. We'll move gently through this concept, starting with ice cubes melting in your drink, then expanding outward to understand why time itself seems to have a direction. If this quiet exploration of cosmic principles helps you unwind or discover something new, your gentle like and soft subscribe mean more than you know. There's no rush tonight. We'll let these ideas settle naturally as we uncover why the universe prefers certain arrangements over others. Let's begin this peaceful journey into entropy's gentle insistence. Why does the steam from your morning coffee always rise and disappear into the surrounding air, never gathering back into droplets and returning to your cup? There's something quietly fascinating about this simple observation that reveals one of the universe's most fundamental principles at work. As you sit there watching those delicate wisps of vapor spiral upward and fade away, you're witnessing a process that has been happening in exactly the same way for billions of years, following rules so reliable that they govern everything from the cooling of distant stars to the warming of your breakfast. The heat flowing from your coffee into the cooler air around it follows an invisible pathway that nature seems to prefer, a direction that appears built into the very fabric of reality itself. Think about how the warmth spreads outward from your mug, moving through the ceramic into your hands and gradually into the room's atmosphere, never once reversing course to flow back from the cool air into your drink. This isn't just happening because your coffee is hot and the air is cooler, though that temperature difference certainly drives the process. Something deeper is occurring here, something that connects this humble kitchen moment to cosmic principles that shape galaxies and determine the fate of the universe. When you add ice cubes to a cold drink on a warm day, they melt predictably, their solid structure dissolving into liquid that mingles with the rest of your beverage. The ice never spontaneously reforms from that mixed liquid, never suddenly separates itself back into perfect crystalline cubes floating at the surface. The melting happens in one direction only, just like the steam rising from your coffee, just like heat flowing from your warm hands to a cool doorknob, just like countless other everyday processes that surround us with their gentle inevitability. These aren't isolated phenomena, but expressions of a universal tendency that operates at every scale, from molecules bouncing in your coffee cup to the expansion of space itself. The remarkable thing is how this directional preference emerges without any external force pushing things along a predetermined path. Your coffee doesn't cool because some cosmic hand is guiding heat away from it. The ice doesn't melt because mysterious forces are dismantling its crystal structure. Instead, these processes unfold naturally, following statistical patterns that arise from the behavior of countless invisible particles, each one obeying simple rules that somehow add up to the complex, directional phenomena we observe. When you breathe on a cold window and watch your warm exhale fog the glass, you're seeing the same principle at work. The moisture in your breath doesn't magically appear on the glass, then evaporate back into your lungs. It moves in one direction, from the warm, humid air you exhale to the cool, dry surface of the window. This directionality appears in chemical reactions too. When you light a match, the wood and chemicals transform into ash, smoke, and heat in a process that never reverses itself. The ash doesn't spontaneously reassemble into a fresh match, complete with its red phosphorus tip ready to strike again. The universality of this pattern extends beyond your immediate experience to encompass all natural processes everywhere. Stars burn their nuclear fuel in one direction, gradually converting lighter elements into heavier ones while radiating energy into space. Rivers flow downhill toward the sea, not uphill toward mountain peaks. Salt dissolves in water far more readily than it crystallizes back out. Perfume spreads through a room rather than concentrating itself back into the bottle. Each of these examples shares that same mysterious quality. They happen easily in one direction, but seem impossible in reverse. The fascinating aspect is that this directional preference isn't written into the fundamental laws of physics themselves. If you could somehow watch individual molecules colliding and bouncing off each other, their microscopic dance would look equally natural whether you viewed it forward or backward in time. The equations governing their motion work the same way in either temporal direction. Yet somehow, when billions upon billions of these reversible microscopic interactions combine together, they produce macroscopic behaviour that flows in only one direction. This emergence of directional time from seemingly symmetric underlying processes represents one of physics' most beautiful puzzles. As you finish your coffee and feel the warmth spreading through your body, you're participating in this grand cosmic tendency. Your body is using the chemical energy in your food to maintain its organised structure while radiating heat into your surroundings. The warmth from your metabolism flows outward into the world, never inward from the environment to spontaneously increase your body temperature. Every breath you take, every heartbeat, every thought represents your temporary resistance to this universal drift while ultimately contributing to it. Understanding why this directionality exists, why nature prefers certain arrangements over others, opens doors to comprehending time itself and our place within the cosmos. Have you ever wondered why certain events in nature seem locked into a single direction, as if time itself has a preferred pathway that forbids any backward journey? When you spray perfume in one corner of a room, its molecules begin an inevitable migration throughout the entire space, dispersing and diluting until the scent becomes evenly distributed everywhere. Yet despite waiting hours, days, or even years, those fragrance molecules never spontaneously gather themselves back into their original concentrated cloud, never reverse their expansion to recreate that initial burst of intensity you first released. This one-way shifting represents something far more profound than simple molecular movement. It reveals a fundamental asymmetry woven into the fabric of existence itself. Consider what happens when you crack an egg into a hot pan, watching the clear albumin transform into opaque white protein, while the yolk spreads and solidifies. The cooking process moves inexorably forward, creating new textures, flavours, and chemical structures that define your breakfast. No amount of cooling, stirring, or wishful thinking can reverse this transformation, cannot persuade those cooked proteins to untangle themselves back into their original liquid state, cannot convince the scrambled mixture to separate back into distinct yolk and white. The impossibility of unscrambling feels so obvious that we rarely question it, yet this everyday limitation points towards something extraordinary about how our universe operates. Think about dropping a delicate glass ornament onto a hardwood floor, watching it shatter into countless fragments that scatter across the room with tiny musical chimes. Each piece follows the laws of physics perfectly as it bounces, slides, and comes to rest in a seemingly random pattern. Those same laws that govern the breaking should theoretically allow the reverse process. All those fragments spontaneously leaping from the floor, fitting themselves back together with perfect precision, and reassembling into the original ornament hovering momentarily before settling gently into your palm. Physics contains no fundamental prohibition against such reconstruction, yet we never observe it happening. The fragments remain scattered until someone deliberately collects and attempts reconstruction, which inevitably reveals that some pieces have chipped further, some have slid under furniture, and perfect restoration has become impossible. These observations extend beyond household accidents to encompass virtually every process we encounter. Burning logs transform into ash, smoke, and heat energy, but ash never spontaneously reorganizes itself back into living wood complete with cellular structure and stored chemical energy. Ice cream melts into a puddle of sweet liquid on a warm day, yet no amount of ambient cooling will cause that puddle to spontaneously freeze back into the original scooped shape with its distinctive swirls and texture. Rust slowly consumes iron surfaces, converting shiny metal into reddish oxide, but rusty metal never spontaneously sheds its oxidation to reveal pristine surface underneath. Each example demonstrates the same puzzling pattern. Processes that flow easily in one temporal direction encounter seemingly insurmountable barriers when attempting reversal. What makes this pattern so intriguing is that it appears to contradict our understanding of fundamental physical laws. If you could observe individual atoms and molecules interacting, their collisions and movements would look equally natural whether viewed forward or backward through time. Microscopic physics shows perfect symmetry regarding temporal direction, with no inherent preference for past versus future. Newton's equations of motion work identically well when time runs forward or backward. The electromagnetic forces governing chemical bonds operate without temporal bias. Quantum mechanical interactions preserve their mathematical elegance regardless of time's direction. Yet somehow these symmetric microscopic interactions combine to create overwhelmingly asymmetric macroscopic behaviour. The mystery deepens when we realise that this directional preference isn't merely inconvenient, but appears absolutely fundamental to how complexity, organisation, and life itself can exist. Without this temporal asymmetry, structures couldn't form, energy couldn't flow in useful ways, and information couldn't accumulate. The very possibility of building anything, learning anything, or experiencing anything depends on processes having preferred directions. Memory formation requires that brain states change in response to experience without spontaneously reverting to previous configurations. Growth requires that biological systems add complexity over time, rather than randomly dismantling themselves. Even consciousness itself seems to depend on this directional flow, as our sense of identity relies on accumulated experiences building upon each other, rather than dissolving back into previous states. This raises a profound question that connects kitchen observations to cosmic principles. Why does disorder consistently triumph over organisation? Why does spreading defeat concentration? Why does mixing overcome separation? The answer involves understanding how probability works when applied to astronomical numbers of particles, how information becomes irretrievably lost during the physical processes, and how time's arrow emerges from fundamentally reversible interactions through purely statistical mechanisms that operate with mathematical certainty. What kind of certainty could be so absolute that it applies to every corner of the universe, yet emerges not from rigid mechanical laws, but from the gentle mathematics of probability? When we say that heat always flows from hot to cold, that perfume always spreads rather than concentrates, that eggs always scramble rather than unscramble, we're invoking a type of inevitability that feels almost magical in its reliability. This isn't the deterministic certainty of a clock's gears turning, or a planet following its orbital path, where mechanical forces drive predictable outcomes through direct cause and effect. Instead, it's a statistical certainty that emerges from the collective behaviour of countless particles, each following simple rules that somehow combine to create universal patterns we can trust with complete confidence. The remarkable aspect of this always is its scope and consistency across all scales of existence. From the smallest molecular interactions happening inside your cells right now to the largest stellar processes occurring in distant galaxies, the same directional preferences assert themselves with unwavering persistence. Bacteria in a drop of pond water experience the same thermodynamic constraints as massive stars burning hydrogen into helium millions of light years away. The coffee cooling on your kitchen table follows identical principles to the gradual cooling of entire planets as they radiate energy into space. Chemical reactions in your body's metabolism proceed according to the same statistical rules governing reactions in laboratory flasks, industrial reactors, and the nuclear furnaces powering our sun. This universality suggests something fundamental about reality itself, something that transcends specific circumstances and operates as a basic feature of how existence functions. Yet here lies the truly puzzling element. When physicists examine the fundamental equations describing how matter and energy behave at their most basic level, they find no inherent preference for any particular temporal direction. Einstein's theory of relativity treats time as just another dimension. With no built-in arrow pointing toward future or past, quantum mechanics describes particle interactions through mathematical frameworks that work equally well whether time moves forward or backward. The electromagnetic force that holds atoms together shows perfect symmetry regarding temporal direction. Even gravity, which shapes the architecture of galaxies and determines the fate of black holes, operates through equations that remain valid regardless of whether we imagine time flowing forward or in reverse. This creates a profound mystery. How can universally directional, macroscopic behaviour emerge from fundamentally non-directional microscopic laws? The answer lies in understanding how statistical principles operate when applied to systems containing astronomical numbers of particles. Consider a simple analogy involving coin tosses, though the reality involves far more particles than there are atoms in the observable universe. If you toss 10 coins simultaneously, getting all heads or all tails represents a relatively unlikely but not impossible outcome. With 100 coins, achieving perfect uniformity becomes much more improbable. With 1,000 coins, the odds against complete organisation become astronomically small. Now imagine systems containing not thousands but trillions upon trillions of particles, each capable of existing in multiple states, all interacting constantly through random collisions and exchanges. The number of ways these particles can arrange themselves grows so rapidly that certain configurations become not just unlikely but effectively impossible within the lifetime of the universe. This is where statistical certainty transforms into practical inevitability. The always we observe in thermodynamic processes emerges from pure mathematics applied to enormous numbers. When billions of molecules are bouncing around in a container, the probability that they will spontaneously organize themselves into perfectly separated regions becomes so infinitesimally small that it might as well be zero. The system doesn't avoid organization because of any fundamental law forbidding it, but because the overwhelming majority of possible arrangements correspond to what we perceive as mixed or disordered states. The ordered arrangements we might prefer represent such a tiny fraction of all possibilities that random motion essentially never produces them. This statistical foundation provides both the explanation for thermodynamic behavior and a source of deep philosophical comfort. The processes we observe aren't arbitrary or mysterious, but follow mathematical principles we can understand and calculate. The always isn't imposed by some external authority, but emerges naturally from the logic of large numbers operating according to a probability theory. This means we can trust these patterns not because they're enforced by cosmic decree, but because they arise inevitably from the mathematical structure underlying physical reality. Understanding this statistical basis also reveals why apparent violations of thermodynamic principles don't actually threaten the overall framework. In extremely small systems containing only a few such particles, we might occasionally observe behavior that seems to violate our expectations about directional processes. These fluctuations don't represent breakdowns in natural law, but rather illustrate the probabilistic foundation from which our macroscopic certainties emerge. As we explore this mystery further, we'll discover how this statistical approach illuminates not only the behavior of gases and liquids, but also the nature of time itself, the possibilities for life and consciousness, and our place within a cosmos governed by probability. Could there be a deeper meaning to disorder that has nothing to do with the messy state of your bedroom or the scattered papers across your workspace? When most people hear the word entropy, they immediately think of chaos, disorganization, or the tendency for things to become jumbled and untidy over time. This intuitive understanding, while containing a grain of truth, misses the profound mathematical precision that underlies what scientists actually mean when they discuss thermodynamic disorder. Your cluttered desk might appear disorganized to visitors, but from a physics perspective, those books, pens, and documents represent an extraordinarily ordered arrangement compared to what entropy actually measures in natural systems. The distinction lies in recognizing that thermodynamic entropy concerns itself not with human preferences for tidiness, but with fundamental questions about how energy and matter distribute themselves throughout space according to statistical principles. Consider a container filled with gas molecules, each one bouncing around at tremendous speed, colliding with neighbours and container walls in an endless dance of motion. If someone could magically arrange these molecules so that faster ones occupied one region while slower ones gathered in another area, the gas would appear highly organised from a microscopic perspective. Yet this apparently structured configuration would actually possess extremely high entropy, because the temperature difference between regions creates conditions where energy can flow and spread. The organised arrangement becomes thermodynamically disordered precisely because it contains concentrated energy gradients that nature immediately begins to eliminate through molecular mixing and collision. This reveals entropy's true character. It measures how evenly energy distributes itself throughout a system, how uniformly matter spreads through available space, and how thoroughly information about initial conditions gets scrambled during physical processes. A perfectly crystalline solid at absolute zero temperature represents the ultimate in both visual organization and thermodynamic order, because its atoms occupy precise positions with minimal kinetic energy and no capacity for energy redistribution. As temperature increases, those same atoms begin vibrating more vigorously within their crystal lattice, creating thermodynamic disorder even though the crystal structure remains visually pristine and geometrically perfect. The entropy increases not because the crystal looks messy, but because thermal energy provides new ways for the atomic system to arrange and rearrange itself internally. Even more surprisingly, some configurations that appear chaotic or random to human observers actually represent states of relatively low entropy. Imagine gas molecules spontaneously clustering in one corner of their container, leaving the rest of the space empty. This looks disorganized and uneven, violating our expectation that gas should fill its container uniformly. Yet such clustering would actually represent a state of lower entropy than uniform distribution, because the molecules have concentrated themselves instead of spreading out to maximize their positional arrangements. The apparent disorder misleads us because we're focusing on visual patterns rather than the underlying statistical mechanics governing particle behavior. Understanding entropy requires shifting perspective from everyday notions of tidiness toward mathematical concepts involving probability distributions and energy landscapes. When water molecules in a liquid bump and jostle against each other at room temperature, they create what appears to be random motion with no discernible pattern. However, this apparent randomness actually represents a state of high entropy because thermal energy has been distributed as evenly as possible among all the molecular motion available within the liquid phase. If those same water molecules suddenly organize themselves into perfectly aligned rows, moving in synchronized patterns, the liquid would look more orderly to human eyes but would actually possess lower entropy because the synchronized motion represents a highly improbable and unstable arrangement. The key insight involves recognizing that entropy measures the number of microscopic ways a system can arrange itself while maintaining the same macroscopic properties we observe. A hot gas has high entropy not because it looks chaotic, but because countless different microscopic arrangements of molecular positions and velocities can produce the same observable temperature, pressure, and density. Cold gas has lower entropy because fewer microscopic arrangements are consistent with its macroscopic state. This statistical foundation explains why entropy tends to increase over time. Systems naturally evolve toward configurations that can be achieved in the greatest number of ways, and these configurations typically correspond to states where energy and matter have spread out as much as possible. The implications extend far beyond simple physical systems to encompass biological organization, information processing, and even cosmic evolution. Living organisms create intricate structures and maintain complex chemical gradients, appearing to violate entropy's tendency toward energy dispersal. Yet life actually accelerates entropy production by harvesting concentrated energy sources like sunlight or chemical fuel and converting them into more dispersed forms like body heat and waste products. The beautiful organization visible in cells, organs, and ecosystems emerges as a byproduct of processes that increase overall entropy while temporarily concentrating order in local regions through energy expenditure. What if every single particle in existence possesses a secret address that specifies exactly where it sits and precisely how fast it moves at any given instant? This hidden reality operates beneath everything we observe, creating an invisible foundation that determines whether ice melts, whether gases mix, and whether time flows forward rather than backward. Imagine being able to take a snapshot of a single moment and record the exact location plus velocity of every atom in a glass of water, every molecule in the surrounding air, every electron orbiting within nearby materials. Such a complete description would constitute what physicists call a microstate, representing the ultimate level of detail possible in describing a physical system. These microstates change continuously as particles collide, bounce, vibrate, and redistribute themselves through space, creating an ever-shifting landscape of positions and motions that evolves according to the fundamental laws governing matter and energy. The staggering complexity emerges when we consider how many different microstates can exist even in relatively simple systems. Take 20 identical coins scattered across a table, each capable of showing either heads or tails. The total number of possible arrangements equals 2 multiplied by itself 20 times, yielding over 1 million distinct configurations. Yet coins represent an almost trivially simple example compared to real physical systems containing astronomical quantities of particles. A single breath of air contains approximately 25 quintillion molecules, each one possessing 3 spatial coordinates plus 3 velocity components that can vary continuously over enormous ranges. The number of possible microstates for such a system exceeds the total count of atoms in the observable universe by factors so large that our mathematical notation struggles to express them. This combinatorial explosion explains why certain macroscopic behaviors appear inevitable despite emerging from fundamentally probabilistic microscopic processes. Consider a container divided by a removable barrier, with gas molecules initially confined to one side. When the barrier disappears, molecules begin spreading throughout the entire available volume through random thermal motion. Each individual molecule follows Newton's laws perfectly as it bounces off walls and collides with neighbours, yet the collective behaviour produces highly predictable results. After sufficient time, the gas distributes itself uniformly because uniform distribution corresponds to an overwhelmingly larger number of possible microstates compared to any alternative arrangement. The molecules don't choose to spread out, nor does any external force compel their dispersion. Instead, random motion just naturally explores the vast space of possible configurations, and since most configurations involve roughly equal molecular densities throughout the container, uniform distribution emerges as the virtually certain outcome. This statistical inevitability becomes even more dramatic when we consider that the specific microstate occupied by any system at a given moment represents just one possibility selected from an incomprehensibly vast collection of alternatives. Every slight shift in particle positions, every minute, every change in molecular velocities creates a completely different microstate. Yet most of these variations produce identical macroscopic appearances. The water in your morning coffee might be composed of molecules arranged in any of countless different ways, with individual H2O units occupying different locations and moving at different speeds, but all these microscopic variations look identical to your senses because they produce the same temperature, density, and liquid behaviour. Human perception operates at macroscopic scales that automatically average over billions of underlying microscopic details, creating the illusion that matter exists in well-defined states, rather than constantly fluctuating probability distributions. The distinction between microstates and macrostates illuminates why most natural arrangements appear random or disordered to our limited perspective. When gas molecules distribute themselves throughout a container, their positions seem haphazard because we cannot perceive the specific microstate being occupied at any moment. We observe only average properties like pressure and temperature that remain approximately constant even though the underlying microstate changes trillions of times per second through molecular collisions and movements. The apparent randomness reflects our inability to track individual particles rather than any fundamental chaos in their behaviour. Each molecule follows deterministic laws, but the system contains far too many interacting components for humans to predict or observe their detailed evolution. This complexity creates an interesting paradox. The more ways a system can arrange itself microscopically, while maintaining the same macroscopic appearance, the more likely we are to observe that particular macroscopic state. States with fewer corresponding microstates become increasingly improbable as system size grows. A deck of cards provides a familiar analogy, though vastly simpler than real physical systems. A perfectly ordered deck with all cards arranged by suit and value represents just one specific configuration out of the astronomical number of possible arrangements. Random shuffling quickly destroys this special ordering because shuffled configurations vastly outnumber organised ones. Similarly, physical systems naturally evolve toward macrostates that can be achieved through the greatest number of microscopic arrangements, producing the directional behaviour we observe in thermodynamic processes. Understanding microstates reveals why the arrow of time emerges from timeless physical laws, and why complexity tends to dissolve into simplicity rather than the reverse. How can billions of invisible particles, each following its own chaotic trajectory, combine to create the stable, predictable properties we measure with thermometers, pressure gauges, and scales? The answer lies in understanding how our limited human senses automatically perform a kind of statistical average, or statistical averaging that transforms the bewildering complexity of molecular motion into manageable observations we can comprehend and use. When you measure the temperature of bathwater with your hand, you're not detecting the individual speeds of water molecules bouncing against your skin. Instead, your nerve endings respond to the average kinetic energy of countless molecular impacts, creating a sensory experience that corresponds to what we call warmth or coldness. This biological averaging process mirrors how scientific instruments work. A thermometer registers the collective thermal motion of particles without providing any information about specific molecular velocities or positions at particular moments. The temperature reading represents a macrostate property that emerges from underlying microscopic chaos while remaining remarkably stable and useful for practical purposes. Similarly, when you inflate a bicycle tyre and check its pressure, the gauge responds to the cumulative force created by air molecules constantly bombarding the inner tube surface. Each individual collision transfers a tiny amount of momentum, but the billions of impacts occurring every second create a steady, measurable pressure that depends on molecular density and average kinetic energy, rather than the specific details of any single collision. The pressure reading tells you nothing about which molecules are moving where at any given instant, yet it provides reliable information about the gas's macroscopic state that allows you to predict how the tire will perform. These macrostate descriptions work because they capture statistical patterns that emerge when enormous numbers of particles interact through random processes. Density represents another example of this statistical magic. When you measure how much mass occupies a given volume, you're determining the average spacing between molecules without knowing their exact locations. The molecules might be clustered more densely in some regions and more sparsely in others at the microscopic level, but these local fluctuations average out over volumes large enough to contain millions of particles. The measured density reflects the collective behavior of the molecular ensemble rather than the precise distribution of individual particles at any specific moment. The remarkable stability of macrostate properties emerges from a principle statisticians call the law of large numbers. Just as the average height of people in a large crowd remains fairly constant, even though individuals vary considerably, the macroscopic properties of physical systems stay relatively steady, even though their constituent particles undergo constant chaotic motion. This stability allows us to make reliable predictions and build useful technologies despite our complete ignorance about microscopic details. We can calculate how much energy is needed to boil water without tracking the motion of individual H2O molecules, design engines that convert heat into mechanical work without monitoring specific atomic collisions, and predict chemical reaction rates without following particular reactant molecules through their transformation processes. The relationship between macrostates and their underlying microstates reveals why certain physical processes appear irreversible, while others seem to violate our expectations. Consider two identical containers, one filled with hot gas and another with cold gas. At the microscopic level, each container hosts a unique, constantly changing microstate as molecules zip around at different speeds and directions. However, both containers can be described using the same macrostate variables: temperature, pressure, volume, and density. If we connect these containers and allow gas to mix, the system evolves toward a new equilibrium macrostate characterized by intermediate temperature and uniform density. This final state can be achieved through an astronomical number of different microscopic arrangements, making it overwhelmingly more probable than alternatives like spontaneous separation back into hot and cold regions. The mixing process appears irreversible, not because any fundamental law prevents unmixing, but because the overwhelmingly vast number of mixed microstates makes spontaneous unmixing virtually impossible within any reasonable time frame. Understanding this distinction explains many puzzling aspects of thermodynamic behavior. When ice melts in warm water, the solid crystal structure dissolves into liquid chaos, yet the process follows predictable patterns described by macrostate variables like temperature and heat capacity. The specific way individual water molecules break free from crystal lattice sites and join the liquid phase varies randomly from moment to moment, but the overall melting rate depends only on macroscopic conditions like temperature difference and thermal conductivity. Countless different microscopic pathways can produce the same macroscopic melting behavior, which is why we can predict when ice will disappear without knowing the detailed molecular mechanisms involved. This perspective illuminates why life and consciousness can exist despite the relentless increase of entropy at the microscopic level. Living systems create and maintain complex macrostate organization by channeling energy flows in ways that increase entropy elsewhere, typically by converting concentrated chemical energy into dispersed heat while building temporary biological structures that persist long enough to support growth, reproduction, and information processing. What happens when we flip 10 identical coins that initially all show heads? And why does this simple experiment reveal the mathematical foundation underlying every thermodynamic process in the universe? Imagine arranging 10 pennies on a table with each one displaying its head side upward, creating a perfectly organized configuration that represents complete order in our miniature system. Now suppose we gather these coins, shake them vigorously in cupped hands, and scatter them randomly across the table surface. The likelihood of achieving the original all-heads arrangement again equals 1 chance in 1024 possible outcomes, making it a relatively rare event that becomes increasingly improbable as we repeat the process. More fascinating still, the probability of obtaining exactly 5 heads and 5 tails reaches approximately 25%, making this mixed configuration roughly 250 times more likely than perfect organization. This dramatic difference in probability emerges from pure mathematics rather than any physical bias favoring disorder over structure. The key insight involves counting how many distinct ways we can achieve each possible outcome through different arrangements of individual coins. Getting all heads requires every single coin to land in one specific orientation, providing just one pathway to success among the some 1024 total possibilities. Achieving 5 heads and 5 tails, however, can happen through 2x2 different combinations because we can select any 5 positions for heads, while the remaining 5 automatically become tails. The mathematics of combinations reveals why mixed states dominate. They can be achieved through vastly more pathways than organized states, making them statistically inevitable when chance governs the process. This probability analysis extends beyond coin tosses to illuminate the behavior of gas molecules, chemical reactions, and thermal processes that shape our daily experience. Consider a container holding just 20 gas molecules, each capable of occupying either the left or right half of the available space. Initially confining all molecules to the left side creates a highly organized state equivalent to our all-heads coin arrangement. When we remove the barrier separating the 2 halves, molecules begin moving randomly throughout the container through thermal motion and collisions. The probability that all 20 molecules will spontaneously return to the left side equals approximately 1 in a million, while configurations with roughly equal numbers on each side become overwhelmingly more likely because they can be achieved through thousands of different molecular arrangements. As system size increases, these probability differences become astronomical rather than merely dramatic. A realistic gas sample contains not 20 molecules, but approximately 25 quintillion particles per cubic centimetre at room temperature and atmospheric pressure. The number of ways these particles can distribute themselves throughout available space exceeds the total count of atoms in the observable universe, by factors so enormous that our mathematical notation struggles to express them meaningfully. Spontaneous organisation becomes not just unlikely but effectively impossible within time frames comparable to the age of the cosmos. The probability of finding all molecules clustered in half the container drops to essentially 0 while uniform. Distribution becomes virtually guaranteed because it corresponds to an incomprehensibly vast number of possible microscopic arrangements. This scaling principle explains why thermodynamic laws appear absolute despite emerging from fundamentally probabilistic processes. With small numbers of particles, we might occasionally observe apparent violations of expected behavior as statistical fluctuations produce temporarily organized configurations. However, as particle counts reach macroscopic scales, these fluctuations become negligible compared to the overwhelming statistical preference for energy dispersal and positional randomization. The mathematics ensures that mixed states dominate so completely that organized states virtually never occur through random processes alone. The beauty of this mathematical foundation lies in its universality and precision. Whether we examine gas mixing, heat conduction, chemical equilibration, or stellar evolution, the same probability principles determine which macroscopic behaviors we observe in nature. Systems containing enormous numbers of particles naturally evolve toward configurations that maximize the number of possible microscopic arrangements, producing the directional flow we associate with time's arrow and entropy increase. This statistical inevitability operates without requiring any external guidance or mysterious forces, emerging purely from the mathematics of large numbers applied to systems governed by random interactions. Understanding these probability relationships also illuminates why certain processes require energy input to reverse their natural direction. Creating organized states from random configurations demands that we bias the process away from its natural statistical preferences, requiring work to overcome the mathematical odds favoring disorder. Refrigerators create temperature differences by expending electrical energy to pump heat against its natural flow direction. Living organisms maintain complex biological structures by consuming chemical fuel that powers organizational processes while producing waste heat. These examples demonstrate how energy expenditure can temporarily overcome statistical tendencies while ultimately contributing to overall entropy increase through the generation of dispersed thermal energy that increases the total number of accessible microstates in the broader environment. What revolutionary insight allowed a 19th century Austrian physicist to connect the abstract mathematics of probability with the concrete reality of steam engines, melting ice, and cooling coffee. Ludwig Boltzmann possessed a uniquely brilliant mind that could perceive hidden relationships between seemingly unrelated phenomena, bridging the gap between the chaotic microscopic world of individual atoms and the predictable macroscopic realm of everyday thermodynamic processes. His groundbreaking realization transformed our understanding of entropy from a vague concept about energy degradation into a precise mathematical quantity that could be calculated, predicted, and applied to virtually any physical system containing large numbers of particles. Before Boltzmann's work, scientists knew that heat flowed from hot objects to cold ones, that gases expanded to fill available space, and that concentrated substances tended to disperse throughout their surroundings, but they lacked a fundamental explanation for why these processes exhibited such universal directional preference. Boltzmann recognized that the answer lay not in mysterious forces or hidden mechanisms, but in the statistical behavior of enormous collections of particles undergoing random motion according to Newton's laws of mechanics. His profound insight involved realizing that entropy directly measures the logarithm of the total number of microscopic arrangements available to a system, providing a bridge between the invisible world of molecular motion and the observable properties we can measure with scientific instruments. The mathematical expression of this insight takes the elegant form S equals K times the natural logarithm of d, where S represents entropy, K stands for Boltzmann's constant, and W denotes the number of microscopic configurations consistent with the system's current macroscopic state. This deceptively simple equation contains extraordinary depth because it quantifies exactly how probability translates into thermodynamic behavior. The logarithmic relationship ensures that entropy increases dramatically as the number of available microstates grows, reflecting the exponential explosion of possibilities that occurs when systems become larger, or when energy spreads throughout more degrees of freedom. Boltzmann's constant serves as a fundamental conversion factor that translates pure numbers of arrangements into energy units, connecting abstract statistical mechanics with practical thermal phenomena like temperature changes and heat flow rates. Understanding this formula requires appreciating why W represents such a crucial quantity in describing physical systems. When ice melts into liquid water, the rigid crystal structure that constrains H2O molecules to specific lattice positions dissolves into fluid chaos where molecules can occupy countless different locations and move with diverse velocities. The solid state corresponds to a relatively small number of possible microscopic arrangements because molecular positions remain largely fixed, while the liquid state permits an astronomically larger number of configurations as molecules gain freedom to explore space and exchange kinetic energy through collisions. Boltzmann's formula captures this transformation by assigning higher entropy to the liquid phase, reflecting its vastly greater number of accessible microstates compared to the crystalline structure. The logarithmic nature of the relationship becomes essential when dealing with realistic systems containing macroscopic quantities of matter. Consider a container holding just 1 mole of gas, approximately 600 billion trillion molecules bouncing around through thermal motion. The number of ways these particles can arrange themselves in space and distribute their kinetic energies among different velocity ranges exceeds imagination, requiring numbers with hundreds of digits to express adequately. Taking the logarithm of such enormous quantities yields manageable entropy values that scientists can calculate, compare, and use in practical applications like predicting chemical reaction rates or designing efficient heat engines. This mathematical transformation converts the overwhelming complexity of microscopic reality into comprehensible macroscopic properties that follow predictable patterns and obey useful equations. The beauty of Boltzmann's insight extends beyond mere mathematical convenience to reveal profound connections between information theory, probability, and the fundamental nature of time itself. Systems naturally evolve towards states characterized by maximum entropy, because these states can be achieved through the greatest number of microscopic pathways. This statistical preference creates the directional flow we observe in thermodynamic processes, where concentrated energy disperses, separated substances mix, and temperature differences equilibrate over time. The formula shows why these processes appear irreversible. Reversing them would require systems to spontaneously transition from high entropy states achievable through countless microscopic arrangements to low entropy states achievable through very few arrangements, making such reversals virtually impossible through random motion alone. Boltzmann's work also illuminates why life and consciousness can exist in a universe governed by entropy increase. Living organisms create local regions of reduced entropy by constructing complex molecular machinery, maintaining concentration gradients, and processing information through neural networks. However, these biological achievements require constant energy expenditure that ultimately increases entropy elsewhere through metabolic heat production and waste generation. The formula quantifies this trade-off, showing how temporary decreases in local entropy can coexist with overall entropy increase throughout the broader environment. This understanding provides a statistical foundation for comprehending how organized complexity emerges and persists within systems that follow fundamental thermodynamic laws, revealing life as a beautiful example of statistical mechanics operating at the intersection of order and chaos. How can pure chance transform into mathematical certainty when enough particles participate in the cosmic dance of thermal motion? The transformation from probability to inevitability occurs through a principle so fundamental that it governs everything from the air you breathe to the nuclear fusion powering distant stars, revealing why macroscopic systems behave with such reliable predictability despite being composed of countless chaotic microscopic interactions. Consider the staggering scale involved when we examine even modest amounts of ordinary matter. A single breath of air contains approximately 25 quintillion molecules, each one bouncing around at supersonic speeds, colliding billions of times per second with neighbours and container walls in an endless frenzy of random motion. This number dwarfs human comprehension, exceeding the total count of grains of sand on all Earth's beaches, surpassing the number of stars in thousands of galaxies, representing a quantity so vast that our minds struggle to grasp its magnitude. Yet this represents just 1/22nd of your respiratory intake, a trivial sample compared to the astronomical particle counts present in any macroscopic object surrounding you right now. When Avogadro's number reveals that 1 mole of any substance contains over 600 billion trillion individual particles, we glimpse the true scale underlying everyday thermodynamic phenomena. A glass of water holds approximately 55 moles of H2O molecules, meaning it contains roughly 30 billion trillion individual particles, each one capable of occupying different positions, moving at various speeds, and interacting with countless neighbours through electromagnetic forces. The number of ways these molecules can arrange themselves throughout the available space exceeds the total number of atoms in the observable universe raised to astronomical powers, creating combinatorial explosions that render certain configurations essentially impossible despite being mathematically permissible. This scale effect explains why spontaneous unmixing becomes not just unlikely but absolutely impossible within any realistic time frame. Imagine opening a bottle of perfume in one corner of a room and waiting for its molecules to spontaneously gather back into their original concentrated location. With macroscopic quantities of fragrance molecules spreading throughout the available air volume, the probability of spontaneous reconcentration becomes so infinitesimally small that it would never occur even if we waited billions of times longer than the current age of the universe. The mathematics isn't prohibiting this reversal through fundamental laws, but simply making it statistically impossible through the overwhelming preference for dispersed arrangements that can be achieved through vastly more microscopic configurations than concentrated ones. The comfort we derive from thermodynamic predictability emerges from this transformation of chaos into order through statistical averaging over enormous particle populations. Individual molecules behave completely randomly, following Newton's laws through unpredictable collision sequences that would challenge even the most powerful computers to simulate accurately. Yet when billions upon billions of these random motions combine together, they produce macroscopic behaviors that follow precise mathematical relationships we can trust with complete confidence. Gas pressure remains steady because molecular impacts against container walls average out over timescales much longer than individual collision intervals. Temperature measurements stay consistent because thermal motion creates statistical distributions that remain stable, even though individual particle velocities fluctuate wildly from moment to moment. This statistical foundation provides profound philosophical reassurance about living in an apparently chaotic cosmos, governed by quantum uncertainty and classical randomness. While we cannot predict the detailed behavior of individual atoms or anticipate specific molecular trajectories, we can rely completely on the aggregate behaviors that emerge when astronomical numbers of particles interact according to probability theory. The laws of thermodynamics represent not arbitrary impositions but inevitable consequences of statistical mechanics applied to realistic physical systems. Heat will always flow from hot objects to cold ones, gases will always expand to fill available volumes, and chemical reactions will always proceed toward equilibrium states, because these macroscopic phenomena reflect overwhelmingly probable outcomes when countless microscopic possibilities combine through random processes. Understanding this scale dependence also illuminates why life and consciousness can flourish within systems governed by entropy increase. Biological organisms contain roughly 10 trillion cells, each one hosting billions of molecular machines that process energy and information with remarkable precision. These cellular processes appear to violate thermodynamic expectations by creating complex structures and maintaining organized states, yet they actually accelerate overall entropy production by converting concentrated chemical fuels into dispersed thermal energy while temporarily building biological complexity through energy-driven assembly processes. The vast numbers of molecules involved in metabolism ensure that biochemical reactions follow predictable statistical patterns, even though individual molecular interactions remain fundamentally random. This perspective reveals existence as a beautiful balance between chaos and order, where randomness at microscopic scales produces reliability at macroscopic scales through purely mathematical principles. The universe operates according to statistical laws that become increasingly certain as system sizes grow, creating stable platforms upon which complexity, information processing, and conscious experience can emerge and persist despite the underlying foundation of quantum uncertainty and thermal fluctuation. What kind of cosmic forgetting occurs when physical processes erase the detailed history of how things came to be? And why does this information loss represent the true driving force behind entropy's relentless increase? When you crack an egg into a hot frying pan and something far more profound than simple cooking takes place, the universe begins losing track of the specific arrangement that existed moments before as the clear boundaries between yolk and white dissolve into a scrambled mixture whose original configuration becomes irretrievably forgotten. This isn't merely inconvenient for breakfast preparation, but represents a fundamental aspect of how reality operates at its deepest level, where information serves as the hidden currency that determines which processes can occur and which remain forever impossible. Consider what happens when you drop a single droplet of blue food colouring into a glass of clear water, watching the concentrated pigment slowly disperse throughout the liquid until it achieves uniform pale blue throughout the entire volume. At the molecular level, billions of dye molecules begin their chaotic journey through the water, each one following a unique pathway as it bounces off H2O molecules and gradually spreads from its initial concentrated location. The mixing process appears straightforward, yet something irreplaceable disappears during this transformation: the precise information about where each dye molecule originated and which specific route it followed during dispersion. Once the mixing completes and uniform coloration emerges, the water contains no remaining traces of the initial droplet's location or the detailed history of how the individual molecules migrated throughout the available space. The information describing the original concentrated state has been scrambled beyond recovery, distributed among countless molecular positions and velocities in ways that cannot be unscrambled through any practical process. This information loss explains why you cannot unburn paper by somehow reversing the combustion reaction that transforms cellulose fibers into ash, carbon dioxide, and water vapor. When paper burns, the organized molecular structure that defined its physical properties gets broken down into simpler chemical compounds that disperse throughout the surrounding environment. The specific arrangement of cellulose chains, the precise positioning of lignin molecules, the detailed architecture of fiber networks all become lost as thermal energy drives chemical bonds apart and creates new molecular configurations. The combustion products carry no memory of their original organization, no blueprint that could guide reassembly back into the complex hierarchical structure that constituted paper. Even if we could somehow gather all the scattered reaction products and supply the necessary energy to drive chemical processes backward, we would lack the crucial information needed to recreate the original material's intricate organization. The gentle tragedy of irreversible information loss extends beyond simple physical mixing to encompass virtually every process we observe in nature. When glaciers melt due to climate warming, the ancient ice crystals that preserve detailed records of atmospheric conditions from thousands of years ago, dissolve into liquid water that retains no memory of its crystalline past. The bubbles of prehistoric air trapped within ice cores, the isotopic signatures that revealed past temperature fluctuations, the microscopic particles that recorded volcanic eruptions and dust storms, all become erased as thermal motion destroys the organized structure that maintained these historical archives. The melting process doesn't violate any conservation laws, as mass and energy remain perfectly accounted for throughout the transformation. Yet something precious disappears forever. The information content that made those ice samples invaluable to climate researchers studying Earth's environmental history. Understanding information as entropy's fundamental currency illuminates why certain processes appear impossible, even when they don't violate basic physical laws. The molecules composing a shattered wine glass contain exactly the same mass and chemical composition, whether arranged as intact glassware or scattered fragments across the floor. Energy conservation doesn't prohibit the fragments from spontaneously reassembling into their original configuration, yet such reconstruction never occurs because the information specifying the glass's original molecular arrangement was lost during the breaking process. Each fragment carries only local information about its own structure, with no knowledge of how it once connected to other pieces or what role it played in the original object's overall organization. The shattering irreversibly scrambled the positional information that defined the glass's functional form, making reconstruction impossible without external guidance that somehow preserves or reconstructs the missing organizational details. This perspective reveals why entropy increase reflects information degradation rather than simple energy dissipation. Physical systems naturally evolve towards states that can be achieved through the greatest number of microscopic arrangements, because these states correspond to maximum information loss about initial conditions. High entropy configurations retain minimal traces of their historical origins, while low entropy states preserve detailed information about the specific processes that created them. Life and consciousness represent remarkable exceptions to this general trend, creating temporary islands of reduced entropy by actively processing and preserving information through energy-driven mechanisms that maintain organized structures while exporting disorder to their surroundings. What invisible force compels concentrated energy to abandon its organized states and disperse throughout space like water flowing downhill? And why does this universal tendency create such breathtaking beauty while simultaneously driving the cosmos toward ultimate thermal equilibrium? The answer reveals itself in understanding how energy behaves according to statistical principles that favor spreading over concentration, dispersal over accumulation, and equilibrium over imbalance through processes so fundamental that they operate identically whether we examine steam rising from your morning tea or nuclear fusion occurring within stellar cores billions of light years away. When you place a hot metal spoon into cold soup, thermal energy begins its inevitable migration from the concentrated high-temperature region within the utensil toward the cooler liquid surrounding it, following pathways that always lead from areas of greater energy density toward regions of lower energy concentration. This isn't happening because some cosmic rule demands heat transfer from hot objects to cold ones, but because molecular kinetic energy naturally seeks statistical arrangements that can be achieved through the greatest number of microscopic configurations. The faster-moving molecules in the hot spoon possess concentrated thermal energy that represents a relatively improbable state compared to the vast number of ways that same energy could distribute itself throughout the entire spoon soup system. As collisions occur at the interface between metal and liquid, high-energy molecules transfer their excess kinetic motion to lower-energy neighbours, gradually creating a more uniform temperature distribution that corresponds to maximum entropy and minimum energy concentration. This dispersal process continues until thermal equilibrium emerges, eliminating temperature gradients and establishing the most statistically probable energy distribution possible under the given constraints. The beauty of this fundamental tendency becomes apparent when we observe how energy dispersal creates the dynamic patterns that animate our world. Ocean currents arise because solar heating creates temperature differences between tropical and polar regions, driving massive circulation patterns that transport thermal energy toward the poles while carrying cooler water toward the equator. These magnificent flows wouldn't exist without energy concentration gradients created by uneven solar heating. Yet their very existence works to eliminate those same gradients through mixing and thermal exchange. Atmospheric weather systems follow similar principles, with concentrated solar energy at Earth's surface creating temperature and pressure differences that drive winds, storms, and precipitation patterns, the swirling hurricanes, towering thunderstorms, and gentle breezes that shape our climate all represent energy dispersal mechanisms working to eliminate thermal imbalances while creating spectacular displays of fluid dynamics in the process. Even life itself emerges as a beautiful manifestation of energy's tendency to spread, with biological organisms serving as temporary channels that accelerate energy dispersal while creating organized complexity as a byproduct. Plants capture concentrated solar energy through photosynthesis, converting electromagnetic radiation into chemical bonds that store energy in molecular form. Yet this apparent concentration actually facilitates energy dispersal by creating food webs that distribute stored energy throughout ecosystems via consumption, metabolism, and heat production. Animals consume plant material or other animals, breaking down complex molecules and releasing their stored energy as thermal motion that ultimately radiates into space as infrared radiation. The intricate beauty of ecological relationships, from pollination networks to predator-prey dynamics, emerges from energy flows that connect all living systems while contributing to universal entropy increase through metabolic heat generation. This perspective transforms our understanding of natural phenomena from collections of separate events into manifestations of a single underlying principle that governs everything from quantum interactions to galactic evolution. Stars represent massive energy dispersal engines that convert concentrated gravitational potential energy into electromagnetic radiation through nuclear fusion, illuminating the cosmos while gradually exhausting their fuel supplies and evolving toward thermal equilibrium with their surroundings. Galaxies rotate and evolve as gravitational energy drives complex dynamics that ultimately lead toward maximum entropy configurations. Even black holes, seemingly the ultimate energy concentrators, actually accelerate entropy production by converting matter into Hawking radiation that disperses throughout space at the maximum possible rate according to thermodynamic limits. The march toward equilibrium operates on cosmic timescales that dwarf human experience, yet its effects manifest in countless ways throughout our daily lives. The gradual cooling of freshly baked bread, the settling of sediments in still water, the fading of colours in sunlight-exposed fabrics all reflect energy dispersal processes working to eliminate concentration gradients and approach statistical equilibrium. Finding beauty in this fundamental drive toward balance requires recognizing that temporary energy concentrations enable all the complexity, organization, and dynamic phenomena we cherish, while ultimately contributing to universal thermal equilibration. The universe appears to be slowly but inevitably evolving toward a state of maximum entropy, where all energy becomes uniformly distributed at the same low temperature throughout space, yet this distant fate doesn't diminish the extraordinary richness that emerges during the long journey toward equilibrium. Our existence occurs during a special epoch when energy concentrations remain sufficient to power stellar fusion, planetary dynamics, chemical evolution, and biological complexity, creating a brief window of cosmic time when matter can organize itself into patterns capable of contemplating their own existence within the grand context of energy dispersal and entropy increase. Why does the simple act of preparing dinner provide such a perfect demonstration of entropy's fundamental principles? And how do the familiar processes unfolding in your kitchen reveal the same thermodynamic laws that govern stellar evolution and galactic dynamics? Every moment you spend cooking offers intimate encounters with energy dispersal, irreversible chemical transformations, and information loss that mirror the cosmic processes shaping our universe on vastly larger scales. When you ignite a gas burner beneath a saucepan, concentrated chemical energy stored in hydrocarbon molecules begins its inevitable journey toward maximum dispersion through combustion reactions that convert methane and oxygen into carbon dioxide, water vapor, and thermal motion. The blue flame represents a region where chemical bonds break and reform in configurations that release stored energy as heat and light, creating temperature gradients that drive subsequent energy transfers throughout your kitchen environment. This thermal energy cannot remain concentrated at the burner, but immediately begins flowing outward through conduction, convection, and radiation pathways that distribute heat through the metal cookware, into the food being prepared, and eventually throughout the surrounding air until equilibrium temperatures emerge across the entire system. The irreversible nature of these energy flows creates the temporal structure that makes cooking a fundamentally directional process, where ingredients transform through predictable sequences that never reverse themselves spontaneously. Consider what happens when you crack eggs into a heated pan, watching the clear albumin proteins unfold and coagulate as thermal energy disrupts the molecular structures that maintain their original liquid transparency. The cooking process involves breaking hydrogen bonds, altering protein conformations, and creating new intermolecular interactions that produce the white, solid texture characteristic of cooked eggs. These chemical changes occur in one direction only because the original protein structures represented organized arrangements that become scrambled beyond recovery as thermal motion increases molecular disorder. The denatured proteins cannot spontaneously refold into their native configurations because the information specifying those precise molecular geometries gets lost during the heating process, scattered among countless possible conformations that look identical at macroscopic scales but differ dramatically in their microscopic arrangements. This transformation illustrates how entropy increase manifests through information loss that makes certain processes irreversible despite perfect conservation of mass and energy throughout the reaction. The one-way progression from raw ingredients to finished meals demonstrates entropy's role in creating time's arrow through accumulating irreversible changes that mark temporal progression. When you saute vegetables, their cellular structures break down as heat, disrupts cell walls, releases internal moisture, and triggers chemical reactions that develop new flavors through Maillard browning and caramelization processes. Each of these transformations moves the system toward higher entropy by converting organized biological structures into more random arrangements, while creating volatile compounds that disperse throughout the kitchen atmosphere. The appealing aromas emerging from your cookware represent molecules that have gained enough thermal energy to escape liquid and solid phases, spreading through available airspace according to diffusion processes that always lead from concentrated sources toward uniform distribution. These scent molecules never spontaneously gather back into their original locations within the food because such reconcentration would require an astronomically improbable reversal of countless individual molecular trajectories. The comfort we derive from cooking's predictability emerges from entropy's statistical certainty when applied to macroscopic systems containing enormous numbers of the particles. You can confidently expect water to boil at specific temperatures, oils to heat at predictable rates, and chemical reactions to proceed according to established timeframes because these processes reflect statistical averages over billions of molecular interactions that follow thermodynamic laws with mathematical precision. Individual molecules behave chaotically and unpredictably, yet their collective behavior produces reliable patterns that enable successful meal preparation through reproducible techniques and timing. This reliability doesn't arise from rigid mechanical determinism, but from statistical principles that become virtually certain when enormous particle populations interact according to probability distributions governed by temperature, pressure, and concentration gradients. Understanding kitchen thermodynamics also reveals how energy expenditure enables temporary decreases in local entropy while contributing to overall increase throughout the broader environment. When you organize ingredients, follow recipes, and create structured presentations, you're investing energy to reduce disorder within the food system while generating heat, waste products, and dispersed energy that increase entropy elsewhere. The metabolic energy your body expends during cooking, the electrical or gas energy consumed by appliances, and the thermal energy dissipated into your kitchen all represent entropy production that enables the temporary organization visible in your finished dishes. This perspective transforms meal preparation from mundane necessity into participation in fundamental cosmic processes where local complexity emerges through energy-driven organization while contributing to universal entropy increase. The kitchen becomes a laboratory for observing how statistical mechanics operates at human scales, revealing the mathematical principles that connect molecular motion to macroscopic phenomena through processes that create beauty, nourishment, and satisfaction, while illustrating the deep connections between everyday experiences and the fundamental laws governing our universe's evolution toward thermal equilibrium. How do living organisms manage to create exquisite complexity, maintain intricate molecular machinery, and build elaborate structures while existing within a universe where entropy relentlessly increases and organization naturally dissolves into chaos? The answer reveals biology as perhaps the most magnificent example of how temporary reductions in local entropy can emerge through energy-driven processes that ultimately accelerate disorder production throughout the broader environment, creating a beautiful paradox where life simultaneously represents both victory over thermodynamic decay and contribution to universal entropy increase through metabolic heat generation and waste production. Every cell within your body functions as a sophisticated entropy management system that consumes concentrated energy sources like glucose and oxygen, while exporting thermal energy and molecular waste products that increase disorder in surrounding tissues and eventually the external environment. The remarkable molecular machines operating within cellular boundaries, from ATP synthase complexes that capture chemical energy to ribosomal factories that assemble proteins according to genetic instructions, represent extraordinarily organized structures that maintain their functional configurations through constant energy expenditure and molecular replacement cycles. These biological systems achieve local entropy reduction by breaking down high-energy molecules and using the released energy to drive synthetic reactions, active transport processes, and structural maintenance mechanisms that preserve organized cellular architecture against the natural tendency toward molecular randomization and structural degradation. The metabolic networks that power cellular organization illustrate how life exploits energy gradients to create temporary islands of reduced entropy within the broader thermodynamic landscape. When your digestive system breaks down complex food molecules into simpler compounds, it releases chemical energy that becomes available for biosynthetic processes throughout your body. However, this energy utilization involves countless irreversible chemical reactions that generate heat, carbon dioxide, water, and other waste products that carry away more entropy than the organized structures they help create and maintain. The net effect increases total entropy while enabling the construction and preservation of biological complexity through processes that channel energy flows in highly specific directions, determined by evolutionary optimization over millions of years. Photosynthesis provides an even more dramatic example of how living systems can reduce local entropy by harnessing external energy sources to drive organizational processes. Plants capture solar radiation through chlorophyll molecules and convert electromagnetic energy into chemical bonds that store concentrated energy within glucose and other organic compounds. This process assembles simple molecules like carbon dioxide and water into complex carbohydrates while releasing oxygen as a byproduct, creating organized molecular structures from randomly distributed atmospheric gases through energy-driven synthesis reactions. However, photosynthesis operates as an entropy-reducing process only within the narrow confines of plant tissues, while the broader Earth atmosphere-Sun system experiences massive entropy increase as solar nuclear fusion converts organized hydrogen into dispersed helium while radiating enormous quantities of thermal energy throughout space. The growth and development that characterize living organisms demonstrate how biological systems can temporarily reverse entropy through coordinated energy expenditure across multiple organizational levels. When a single fertilized egg develops into a complex multicellular organism containing trillions of specialized cells arranged in intricate tissues and organ systems, the process involves converting simple nutrients into highly organized biological structures through precisely controlled gene expression, protein synthesis, and cellular differentiation. This developmental progression moves from relatively simple initial conditions toward increasingly complex final states, appearing to violate thermodynamic expectations about spontaneous organization. Yet embryonic development requires massive energy inputs from maternal metabolism, environmental resources, and cellular respiration that generate far more entropy than the developing organism represents, ensuring that overall disorder increases throughout the biological system and its environment, while enabling temporary local complexity through energy-subsidized organizational processes. The eventual death of every living organism represents the ultimate return to thermodynamic equilibrium as biological systems lose their ability to maintain energy gradients and organizational structures against entropic decay. When cellular metabolism ceases, the molecular machinery that preserved biological complexity begins decomposing through spontaneous chemical reactions that release stored energy as heat, while breaking down organized structures into simpler compounds. Decomposition processes accelerate entropy production as bacteria and other microorganisms consume biological materials and convert them into carbon dioxide, water, and mineral nutrients that disperse throughout soil and atmospheric systems. This biological recycling returns the concentrated energy and organized matter that characterize the living organism to maximum entropy states, while making those resources available for new cycles of life and growth. Understanding this thermodynamic perspective on mortality provides profound comfort by revealing death as a natural consequence of universal physical laws rather than arbitrary tragedy or mysterious punishment. The beautiful dance between order and disorder in biological systems illuminates life's place within cosmic evolution, showing how temporary complexity can emerge and flourish while contributing to the fundamental processes that drive universal entropy increase and connect living phenomena to the broader thermodynamic principles governing stellar fusion, planetary dynamics, and galactic evolution across all scales of space and time. What lies at the end of time's arrow when the universe completes its slow journey toward maximum entropy? And why should this ultimate fate inspire wonder rather than despair about our current epoch of cosmic complexity and stellar brilliance? The concept of heat death represents not catastrophic destruction, but peaceful equilibration, a state where all energy becomes uniformly distributed throughout space at the same low temperature, eliminating the gradients that currently drive stellar fusion, planetary dynamics, and biological evolution across countless worlds orbiting billions of stars. This final condition doesn't violate any physical laws or represent cosmic failure, but fulfills entropy's fundamental tendency towards statistical maximum, creating a universe where no further energy transfers can occur, because thermal equilibrium has been achieved on the grandest possible scale. Understanding this distant destiny requires appreciating the astronomical timescales involved, measured not in human lifetimes or geological epochs, but in periods so vast that they dwarf even the current age of our cosmos by factors of millions or billions. Stars like our Sun will continue burning hydrogen fuel for approximately 10 billion more years, gradually converting nuclear energy into electromagnetic radiation that propagates throughout space while slowly diminishing stellar mass through Einstein's mass-energy equivalence. Smaller red dwarf stars possess sufficient fuel reserves to maintain fusion reactions for trillions of years, far longer than current estimates for the universe's present age, creating extended periods where stellar energy production can support planetary systems and potentially biological evolution on timescales that challenge human comprehension. Even after stellar fuel becomes exhausted and main sequence burning ceases throughout the galaxy, white dwarf remnants will continue radiating stored thermal energy into space for hundreds of trillions of additional years as they gradually cool toward absolute zero temperatures. The processes leading toward heat death operate through mechanisms both gentle and inexorable, driven by the same entropy increase that governs everyday phenomena like cooling coffee and melting ice, but extended across cosmic scales involving galactic clusters, dark matter halos, and the expanding fabric of space-time itself. Stellar evolution represents a continuous conversion of concentrated gravitational potential energy into dispersed electromagnetic radiation through nuclear fusion processes that transform hydrogen into helium while releasing photons that carry energy away from stellar cores toward interstellar space. This energy dispersal reduces local entropy within stellar interiors, where fusion creates organized helium nuclei from simpler hydrogen protons, yet increases overall entropy as radiated energy spreads throughout the universe and eventually thermalizes with cosmic microwave background radiation left over from the Big Bang. Galaxy mergers and stellar interactions gradually redistribute kinetic energy through gravitational encounters that eject some stars into intergalactic space, while causing others to spiral inward towards central black holes, creating processes that increase entropy through energy dispersal while reshaping galactic architectures over billions of years. Black holes themselves, initially appearing as entropy reducers that concentrate matter into minimal volumes, actually maximize entropy's production through Hawking radiation processes that convert organized matter into thermal radiation at rates proportional to their surface areas. The smallest black holes evaporate fastest through quantum tunneling effects that create particle-antiparticle pairs near event horizons, gradually returning their concentrated mass energy to dispersed radiation that adds to universal thermal background. This evaporation process operates over timescales ranging from microseconds for microscopic black holes to 10^67 years for supermassive galactic centers, ensuring that even these ultimate gravitational concentrators eventually contribute to cosmic entropy maximization through complete energy dispersal. Finding peace in this cosmic destiny requires recognizing that heat death represents fulfillment rather than failure, the natural consequence of statistical mechanics applied to finite energy resources distributed throughout expanding space-time. Our current universe exhibits extraordinary beauty precisely because it exists far from thermal equilibrium, with massive energy gradients between stellar cores and cosmic background radiation driving all the complex phenomena we observe and cherish. Stars shine brilliantly against dark space because nuclear fusion creates temperature differences of millions of degrees between stellar interiors and their surroundings, enabling energy flows that power planetary atmospheres, weather systems, ocean currents, and biological evolution through photosynthesis and metabolic processes. The magnificent spiral structures of galaxies, the dynamic evolution of planetary systems, the chemical complexity that enables life and consciousness all depend on energy gradients that will eventually disappear as entropy approaches its maximum value throughout the cosmos. This perspective transforms our current epoch from ordinary cosmic time into an extraordinarily special period when matter can organize itself into patterns capable of contemplating their own existence within the broader context of universal evolution toward equilibrium. We live during a brief window when concentrated energy sources remain available to power stellar fusion, planetary dynamics, biological complexity, and conscious awareness, creating opportunities for understanding, creativity, and appreciation that may never occur once thermal equilibrium eliminates the energy flows that make organized complexity possible. The approaching heat death doesn't diminish the value or significance of current phenomena, but highlights their precious temporary nature and encourages profound gratitude for existing during this remarkable phase of cosmic history when entropy gradients enable beauty, complexity, and wonder. How can the fundamental equations governing every particle in the universe show perfect indifference to time's direction while producing the overwhelmingly asymmetric world we observe, where eggs scramble but never unscramble, where heat flows from hot to cold but never reverses, and where aging progresses relentlessly forward without ever moving backward? This profound mystery sits at the heart of modern physics, revealing a fascinating disconnect between the mathematical laws that describe reality's deepest level and the everyday phenomena that define our lived experience of temporal flow. When Newton formulated his equations of motion over 3 centuries ago, he unknowingly created mathematical structures that treat past and future as completely equivalent directions in time, with no inherent preference for forward progression over backward movement through temporal dimensions. If you could observe 2 billiard balls colliding and film this interaction, then play the recording in reverse, both versions would appear equally natural from the perspective of Newtonian mechanics, because the forces, accelerations, and momentum transfers involved in the collision obey identical mathematical relationships regardless of temporal direction. The laws governing electromagnetic interactions display similar temporal symmetry, with electric and magnetic fields propagating according to Maxwell's equations that remain mathematically valid whether time increases or decreases. Even quantum mechanics, our most fundamental theory describing atomic and subatomic phenomena, operates through the Schrödinger equation that exhibits perfect time reversal symmetry in its basic mathematical structure, allowing quantum systems to evolve equally well forward or backward through time according to the same probabilistic principles. This symmetry extends to virtually every fundamental physical law scientists have discovered, from conservation of energy and momentum to the detailed balance conditions governing chemical reaction rates. Individual molecular collisions in gases occur through electromagnetic forces that push and pull charged particles according to equations that work identically whether we imagine time flowing forward or backward, creating microscopic interactions that show no inherent temporal bias or directional preference. When 2 molecules approach each other, experience repulsive forces as their electron clouds overlap, and then separate with modified velocities, this entire process could equally well occur in temporal reverse, with the molecules approaching from their final directions, interacting through identical forces and departing along their original trajectories. The mathematical description remains completely valid and physically meaningful in either temporal direction, suggesting that nature's fundamental laws contain no information about which direction corresponds to past versus future. This creates the central puzzle. If individual particle interactions show perfect time symmetry, Why does macroscopic behaviour exhibit such dramatic temporal asymmetry? The resolution involves understanding how statistical properties emerge when enormous numbers of time-symmetric microscopic processes combine together through random interactions that explore the vast space of possible configurations available to large systems, while each individual molecular collision remains perfectly reversible. Collections containing billions or trillions of particles naturally evolve towards states that can be achieved through vastly more microscopic arrangements, making certain macroscopic transitions overwhelmingly probable in one temporal direction, while becoming virtually impossible in the reverse direction. The key insight involves recognizing that time's arrow emerges not from violations of fundamental symmetries, but from statistical principles that operate when time-symmetric laws govern systems containing astronomical numbers of particles. Consider a container initially divided into two chambers, one holding hot gas and another containing cold gas, separated by a removable barrier. When the barrier disappears, molecular motion causes gradual mixing that produces uniform temperature throughout the container, creating a process that appears irreversible despite being composed entirely of reversible molecular collisions. Each collision between hot and cold molecules conserves energy and momentum while following electromagnetic laws that work equally well in reverse. Yet the collective effect produces directional change from separated states toward mixed states because mixed configurations correspond to vastly more possible microscopic arrangements. The apparent irreversibility doesn't arise from asymmetric fundamental laws, but from statistical inevitability when symmetric laws operate on large systems that can explore enormous ranges of possible organizational states. This emergence of temporal asymmetry from symmetric foundations represents one of physics' most beautiful examples of how macroscopic properties can differ qualitatively from the microscopic laws that govern their constituent parts. The time-reversible equations describing individual particle behavior combine through statistical mechanics to produce time-irreversible thermodynamic phenomena, creating temporal flow without requiring any fundamental breaking of time symmetry at the deepest physical level. Understanding this emergence illuminates why attempts to reverse macroscopic processes require such careful manipulation of initial conditions and external energy inputs, as such reversals demand fighting against overwhelming statistical probabilities rather than violating fundamental physical principles. The reversibility paradox thus resolves through appreciating how probability theory transforms symmetric microscopic laws into asymmetric macroscopic behavior through purely mathematical mechanisms that operate with statistical certainty when applied to realistic systems containing vast numbers of interacting particles following time-symmetric dynamics according to conservation laws and force equations that remain equally valid in both temporal directions. What mathematical magic transforms the chaotic dance of countless individual particles into the stable, predictable phenomena we observe at macroscopic scales? And how does this transformation reveal one of nature's most profound examples of emergent complexity arising from statistical principles? The answer lies in understanding how the central limit theorem operates within thermodynamic systems, creating reliable macroscopic behavior from fundamentally random microscopic processes through pure mathematical inevitability that requires no external guidance or mysterious organizing forces. When millions upon millions of gas molecules bounce around inside a container, each following its own unpredictable trajectory through space while colliding randomly with neighbours and walls, their individual motions appear completely chaotic and impossible to track or predict with any precision. Yet somehow these countless random interactions combine to produce measurable properties like temperature and pressure that remain remarkably stable and follow precise mathematical relationships scientists can use to design engines, predict chemical reactions, and understand atmospheric behaviour. This stability doesn't emerge because individual molecules suddenly become predictable or because hidden forces impose order upon molecular motion, but because statistical averaging over enormous particle populations automatically smooths out random fluctuations and produces reliable macroscopic patterns governed by probability distributions. The central limit theorem provides the mathematical foundation for this remarkable transformation, demonstrating that averages computed from large numbers of random variables naturally converge toward predictable values regardless of how chaotic the underlying individual contributions might be. When applied to molecular systems, this theorem explains why properties like average kinetic energy per particle remain nearly constant even though individual particle velocities vary wildly and change continuously through collisions. The temperature of a gas represents precisely such an average quantity, measuring the mean kinetic energy of molecular motion without revealing anything about specific particle velocities at any given moment. As the number of molecules increases, fluctuations in this average become progressively smaller relative to the mean value, creating the stable temperature measurements that enable practical thermodynamics despite the underlying chaos of molecular motion. This averaging process operates across multiple scales simultaneously, creating hierarchical structures where random behavior at one level produces organized patterns at higher levels through purely statistical mechanisms. Individual molecular collisions transfer energy and momentum in seemingly random directions, yet these transfers combine to create predictable diffusion patterns that govern how gases mix, how heat conducts through materials, and how chemical concentration gradients evolve over time. The random walks followed by individual molecules produce macroscopic behavior that follows deterministic differential equations, transforming microscopic chaos into macroscopic order through mathematical principles that require no external intervention or guidance. This emergence represents a profound example of how complex systems can exhibit properties that differ qualitatively from those of their constituent parts, revealing new organizational levels that arise spontaneously from statistical interactions among large numbers of simpler components. The magic becomes even more remarkable when we consider how these statistical principles create entirely new types of stability that don't exist at microscopic scales. Individual molecules possess no inherent temperature because temperature represents a collective property that only emerges when large populations interact through energy exchange processes. A single molecule cannot have pressure because pressure requires statistical averaging over countless molecular impacts against surfaces. These macroscopic properties represent genuinely novel phenomena that arise through statistical mechanics rather than simple summation of microscopic contributions, creating emergent characteristics that enable new types of physical behavior and scientific understanding. This emergence of macroscopic stability from microscopic chaos explains why thermodynamic engines can operate reliably despite being composed of materials containing astronomical numbers of randomly moving particles. Steam engines convert thermal energy into mechanical work through processes that depend on predictable relationships between temperature, pressure, and volume. Yet these relationships emerge from the chaotic motion of water molecules whose individual trajectories remain completely unpredictable. The reliability of thermodynamic cycles doesn't require controlling individual molecular behavior, but it emerges automatically through statistical averaging that creates stable macroscopic properties from random microscopic foundations. Understanding this statistical foundation also reveals why certain macroscopic behaviors appear inevitable, while remaining theoretically reversible at the microscopic level. When hot and cold gases mix to reach uniform temperature, the process appears irreversible because spontaneous unmixing would require an astronomically improbable coordination among countless individual molecular trajectories. The mixing occurs not because individual collisions favour energy dispersal, but because the overwhelming majority of possible molecular arrangements correspond to mixed rather than separated states, making mixing virtually certain through pure probability rather than deterministic forcing. This perspective transforms our understanding of natural processes from mechanical inevitability towards statistical inevitability, revealing how reliable macroscopic behavior emerges from fundamentally probabilistic foundations through mathematical principles that operate with certainty when applied to sufficiently large systems. The wonder lies in recognizing that stable, predictable phenomena arise spontaneously from chaos through purely mathematical relationships that require no external organizing intelligence or mysterious vital forces. Nature achieves organization through statistical mechanics rather than imposed design, creating the reliable physical world we inhabit through emergent properties that arise when simple rules governing individual particles combine through interactions involving astronomical numbers of components following probability distributions that naturally produce macroscopic stability from microscopic randomness. What extraordinary cosmic circumstances could have produced a universe that began in such an improbably organized state? And why does this initial low entropy configuration represent perhaps the greatest unsolved puzzle in modern cosmology? The mystery deepens when we recognize that our entire experience of time's arrow Entropy increase and thermodynamic irreversibility depends fundamentally on the universe having emerged from quintillions of remarkable order rather than the maximum entropy state that statistical mechanics would naturally expect. If the cosmos had begun in thermal equilibrium with energy uniformly distributed throughout space, no temperature gradients would exist to drive stellar fusion, no density fluctuations would create gravitational collapse into stars and galaxies, and no energy flows would enable the complex chemistry necessary for biological evolution and conscious observers capable of contemplating these questions. Instead, our universe appears to have originated from an extraordinarily special initial configuration that contained vast stores of gravitational potential energy, concentrated in an almost perfectly smooth distribution of matter, and radiation that possessed incredibly low entropy despite containing enormous total energy density. The Big Bang represents not a chaotic explosion dispersing matter randomly throughout space, but a highly coordinated expansion that maintained remarkable uniformity while allowing tiny density fluctuations to grow through gravitational amplification over cosmic time. Current observations reveal that the early universe exhibited temperature variations of only 1 part in 100,000 across different regions of space, creating a level of organizational precision that seems almost miraculous when considered from statistical perspectives that would naturally expect random energy distribution rather than such extraordinary coordination. This initial smoothness provided the gravitational potential energy that now powers stellar fusion, galactic rotation, and all the dynamic processes that create complexity throughout the observable cosmos. Yet the physical mechanisms responsible for establishing these special initial conditions remain profoundly mysterious, despite decades of theoretical investigation and observational study. Cosmic inflation offers one possible explanation for the universe's initial low entropy through a hypothetical period of exponential expansion that could have stretched microscopic quantum fluctuations into macroscopic density variations, while maintaining overall smoothness across vast scales. This inflationary scenario suggests that random quantum mechanical processes operating during the universe's earliest moments became amplified through rapid spatial expansion into the large-scale structures we observe today, converting microscopic disorder into macroscopic order through geometric effects that stretched small-scale randomness across cosmological distances. However, inflation itself requires extremely specific initial conditions to operate successfully, merely pushing the mystery of special initial states back to even earlier epochs, without fundamentally resolving the question of why the universe began in such an improbably organized configuration, rather than maximum entropy thermal equilibrium. The fine-tuning required for successful inflation appears almost as extraordinary as the low entropy initial state it attempts to explain, suggesting that the mystery of cosmic origins may involve fundamental aspects of physical law or cosmic evolution that remain beyond current theoretical understanding. Some cosmologists propose eternal inflation scenarios where countless pocket universes emerge from quantum fluctuations in higher dimensional spaces, creating vast multiverses where random statistical processes eventually produce regions with suitable initial conditions for complex evolution despite the overwhelming majority of cosmic volumes remaining in high entropy equilibrium states. These speculative frameworks suggest that our observable universe represents a statistically rare but inevitable outcome when infinite cosmic resources allow exploration of all possible initial configurations through random quantum processes operating over unlimited time and space. However, such multiverse theories raise profound questions about scientific methodology and observational verification, as they invoke unobservable realms that may lie forever beyond experimental investigation or theoretical confirmation. Alternative approaches focus on finding fundamental physical principles that could naturally produce low-entropy initial conditions without requiring fine-tuning or anthropic selection effects, seeking modifications to general relativity, quantum mechanics, or thermodynamics that might explain why the universe began in organized rather than random states. The ultimate resolution may require revolutionary advances in our understanding of quantum gravity, the nature of time itself, or the relationship between physical law and cosmic boundary conditions that operate at scales and energy densities far beyond current experimental capabilities. Until such breakthroughs emerge, the initial conditions mystery remains one of science's most profound unsolved problems, highlighting the limits of current knowledge while inspiring continued theoretical investigation and observational study. Accepting this mystery as temporarily beyond resolution provides opportunities for philosophical reflection about the nature of explanation, the limits of scientific knowledge, and humanity's place within a cosmos whose ultimate origins may involve aspects of reality that transcend our current conceptual frameworks. The beauty of this unsolved puzzle lies not in its intractability, but in its reminder that the universe continues to surprise us with phenomena that challenge our deepest assumptions about causation, probability, and the fundamental nature of physical existence, encouraging humility about the scope of human understanding, while inspiring continued exploration of these cosmic enigmas through advancing theoretical physics and increasingly sophisticated observational astronomy that may eventually illuminate the profound mystery of why time flows forward, rather than remaining eternally balanced in thermodynamic equilibrium. Why do our most vivid childhood memories gradually become hazy and fragmented over time? And what does the unnatural fading reveal about the fundamental thermodynamic principles governing information storage in biological and physical systems? The process of forgetting represents far more than simple neglect or inattention. It illustrates how entropy operates within neural networks, molecular structures, and information storage media to gradually degrade organized patterns that preserve knowledge, experiences, and records of past events. Your brain maintains memories through specific arrangements of proteins, neurotransmitters, and synaptic connections that require constant energy expenditure to preserve against the natural tendency toward molecular randomization and structural decay. Each memory trace exists as a delicate pattern of chemical modifications and cellular architectures that must resist entropy's relentless pressure toward maximum disorder, making memory retention an active process rather than passive storage that automatically persists without metabolic support. The formation of new memories involves encoding information through irreversible chemical reactions that modify synaptic strengths and create new molecular configurations within neural tissues. Yet these same biochemical processes that enable memory storage also make memories vulnerable to thermodynamic degradation over time. As cellular metabolism generates heat and molecular motion disrupts protein structures, memory traces gradually lose their precision and specificity, causing details to blur together, while emotional associations and general patterns tend to persist longer than specific factual content. This selective degradation occurs because different aspects of memory storage involve different molecular mechanisms with varying susceptibility to thermal fluctuation and chemical modification, creating a natural hierarchy where some information remains accessible, while other details become irretrievably lost through entropy-driven processes that operate continuously throughout our lives. The energy cost of maintaining accurate memories becomes apparent when we consider the metabolic requirements of neural tissue, which consumes approximately 20% of our total caloric intake despite representing only 2% of body mass, largely to power the biochemical processes that preserve and access stored information. This enormous energy expenditure reflects the thermodynamic challenge of maintaining organized molecular structures against entropy while simultaneously supporting the dynamic processes required for memory consolidation, retrieval, and integration with ongoing experience. Sleep appears to play a crucial role in memory maintenance by allowing neural systems to perform metabolic cleanup and structural repairs that preserve important information while allowing less significant details to fade through entropy-driven forgetting processes that help optimize storage capacity and prevent interference between competing memory traces. Understanding memory as an entropy-fighting process illuminates why external storage systems face similar challenges in preserving information over extended periods without active maintenance and energy input. Photographs fade because the chemical dyes and silver compounds that create visual images gradually break down through oxidation reactions, ultraviolet radiation exposure, and thermal molecular motion that disrupts the organized arrangements responsible for color reproduction and image clarity. The yellowing of old books results from acid hydrolysis and oxidation processes that degrade cellulose fibers and lignin compounds within paper, demonstrating how entropy operates on molecular scales to destroy the chemical structures that preserve written information for future generations. Even stone inscriptions and metal engravings experience gradual erosion through weathering processes that slowly obliterate carved symbols, showing how entropy challenges information preservation across all physical media, regardless of their apparent durability and resistance to change. Digital storage systems represent humanity's most sophisticated attempt to combat entropy through error correction algorithms, redundant backup systems, and active maintenance protocols that continuously monitor and repair information degradation before it becomes irreversible. Modern computer hard drives, solid-state memory devices, and optical storage media employ complex engineering solutions that detect and correct bit errors caused by thermal fluctuation, electromagnetic interference, and molecular-scale defects that naturally arise in information storage materials over time. Cloud computing architectures distribute data across multiple geographic locations and storage systems, creating redundancy that protects against local entropy increases while requiring enormous energy expenditure to maintain the server farms, cooling systems, and network infrastructure necessary for reliable digital preservation. This technological struggle against entropy reveals information as perhaps the most fragile and valuable resource in our universe, requiring constant vigilance and energy investment to preserve against the natural tendency toward randomization and decay. The bittersweet nature of impermanence becomes apparent when we recognize that forgetting serves important biological functions by preventing our neural systems from becoming overwhelmed with irrelevant details while allowing the essential information to persist through selective preservation mechanisms. The gradual fading of painful memories often brings psychological relief, while the loss of cherished experiences creates poignant reminders of time's passage and life's temporary nature. This natural information decay connects human experience to cosmic processes operating across all scales, from quantum decoherence in atomic systems to stellar evolution and galactic dynamics that gradually erase traces of past events while creating opportunities for new patterns and experiences to emerge through ongoing thermodynamic processes that drive universal entropy increase, while enabling temporary local decreases in disorder through energy-driven organization and information processing systems. Why do even the most carefully planned organizations gradually drift toward confusion and inefficiency without constant management and renewal? And what can thermodynamic principles teach us about the universal challenges of maintaining social order, clear communication, and meaningful relationships? The concept of social entropy provides a powerful lens for understanding how human institutions, collaborative projects, and interpersonal connections naturally tend toward increased randomness, decreased coordination, and diminished effectiveness over time unless deliberate energy is continuously invested to preserve organizational structures and communication clarity. Just as physical systems naturally evolve toward maximum disorder through statistical processes, social systems experience analogous pressures that cause initial enthusiasm to fade, shared understanding to fragment, and collective purpose to become diluted as individual perspectives diverge and external influences introduce new complications. Consider how a startup company begins with crystal clear vision, unified goals, and seamless communication among founding members who share intimate knowledge of the project's purpose and methodology. As the organization grows and incorporates additional personnel, the original clarity becomes increasingly difficult to maintain across expanding networks of collaboration, requiring formal procedures, documentation systems, and management structures to preserve coordination that previously emerged naturally from direct personal interaction. The entropy increase manifests as competing priorities, communication breakdowns, bureaucratic inefficiencies, and gradual drift away from founding principles that once provided clear direction for all organizational activities. Without active leadership that continuously reinforces shared values, clarifies objectives, and maintains communication pathways, even successful organizations tend toward fragmentation and dysfunction through purely natural processes that mirror thermodynamic tendencies toward equilibrium and maximum disorder. Miscommunication represents perhaps the purest example of information entropy operating within social contexts, where precise meanings intended by speakers become degraded, distorted, and misinterpreted as they propagate through chains of human interaction. Transmission of information through verbal communication, written messages, or digital media introduces opportunities for error, ambiguity, and misunderstanding that accumulate over multiple exchanges until original meanings become thoroughly scrambled or completely lost. The children's game of telephone demonstrates this principle dramatically, showing how simple messages become transformed beyond recognition as they pass through sequential interpretation and retransmission processes that introduce random variations at each step. Professional environments experience similar information degradation, when complex instructions, technical specifications, or strategic decisions must be communicated across departmental boundaries, hierarchical levels, and cultural differences that create barriers to accurate information transfer. The energy required to maintain clear communication includes not only the immediate effort of careful articulation and active listening, but also ongoing investments in relationship building, trust development, and shared vocabulary. Creation that provide foundations for accurate information exchange over extended periods. Email chains, meeting minutes, documentation systems, and feedback mechanisms all represent organizational attempts to combat communication entropy by creating redundant information pathways and error correction protocols that preserve meaning, despite the natural tendency toward miscommunication and misunderstanding. Personal relationships exhibit similar entropy-driven challenges that require continuous emotional labor, attention, and intentional effort to maintain intimacy, understanding, and mutual support against natural forces that promote drift, neglect, and gradual disconnection. The initial excitement and effortless connection experienced during early relationship phases gradually gives way to more complex dynamics involving competing schedules, diverging interests, accumulated grievances, and decreased novelty that can erode emotional bonds without deliberate countermeasures. Successful long-term relationships require ongoing investments of time, energy, and attention to preserve shared experiences, maintain open communication, and address conflicts before they become entrenched patterns that resist resolution. Date nights, regular conversations, shared activities, and conscious expressions of appreciation represent relationship maintenance behaviors that combat social entropy by creating new positive interactions while repairing inevitable wear and tear that accumulates through daily stress and routine interactions. The wisdom embedded in understanding social entropy lies in recognizing these challenges as natural consequences of statistical processes rather than personal failures or moral deficiencies, encouraging realistic expectations about the effort required to maintain any form of human organizational connection. Accepting entropy as a fundamental aspect of social dynamics can reduce frustration, guilt, and disappointment that arise when relationships or organizations experience predictable difficulties, while simultaneously highlighting the importance of proactive maintenance behaviors that preserve valuable social structures against natural degradation. This perspective also reveals why sustainable social systems must incorporate mechanisms for renewal, adaptation, and regeneration that acknowledge entropy while channeling its effects in constructive directions through planned obsolescence, scheduled reorganizations, leadership transitions, and cultural evolution processes that allow healthy change while preserving essential functions and values. Understanding social entropy ultimately promotes both humility about human limitations and appreciation for the remarkable achievements possible when deliberate effort successfully creates temporary islands of coordination, understanding, and mutual support within the broader context of natural tendencies toward fragmentation and disorder. What mysterious force enables artists, musicians, writers to harness the creative power of controlled chaos while transforming random inspiration into organized masterpieces that resonate across cultures and centuries? The relationship between entropy and creativity reveals one of the most fascinating applications of thermodynamic principles to human expression, where deliberate manipulation of disorder and uncertainty becomes the driving force behind innovation, aesthetic beauty, and meaningful communication through artistic media. Creative processes operate at the fascinating boundary between complete randomness and rigid structure, utilizing controlled entropy to generate novel combinations of ideas, sounds, images, and words that would never emerge from purely systematic approaches to artistic production. When painters allow watercolors to bleed randomly across wet paper surfaces, they embrace entropy as a collaborative partner that introduces unexpected patterns and color combinations beyond conscious planning or precise control. These accidental effects often become the most compelling elements within finished artworks, suggesting that creativity benefits from incorporating chance events and uncontrolled variables into otherwise purposeful creative endeavors. Jazz improvisation provides perhaps the clearest example of entropy-driven artistic expression, where musicians deliberately abandon predetermined melodies and harmonies in favor of spontaneous responses to musical moments that cannot be fully predicted or controlled in advance. The magic of improvised performance emerges from the tension between musical knowledge and random inspiration, as skilled performers use their technical training to channel unpredictable creative impulses into coherent musical statements that surprise both performers and audiences. This process mirrors thermodynamic systems that achieve beautiful complexity through the interaction of organizing forces and random thermal motion, creating emergent patterns that could never be designed through purely deterministic methods. The most compelling improvisational moments often arise when musicians allow their conscious minds to step aside and permit subconscious processes to guide their artistic choices, creating space for entropy-driven discovery while maintaining sufficient structure to produce meaningful musical communication. Literary creativity demonstrates similar principles through writing processes that combine disciplined craft with openness to unexpected narrative developments, character revelations, and linguistic discoveries that emerge during the act of composition itself. Many accomplished authors describe experiencing surprise at plot developments that seem to arise spontaneously from the creative process, suggesting that successful writing involves creating conditions where entropy can generate novel connections between ideas while maintaining sufficient narrative coherence to engage readers effectively. Stream of consciousness techniques deliberately embrace randomness by allowing thoughts to flow without rigid editorial control, often revealing unexpected associations and insights that more systematic approaches might overlook or suppress. The editing process then applies organizing principles to this raw creative output, selecting and arranging the most promising elements while discarding material that doesn't contribute to overall artistic unity, much like physical sound systems that achieve stable configurations by allowing random fluctuations to explore possible arrangements, while energy considerations determine which configurations persist over time. Visual arts exemplify the creative potential of organized disorder through techniques like action painting, collage construction, and found object assemblage that incorporate random elements while using artistic judgment to create meaningful compositions from initially chaotic materials. Jackson Pollock's drip paintings emerged from carefully controlled random processes where paint application followed physical laws of fluid dynamics and gravity, while the artist's movements introduced intentional variations that shaped overall compositional structure. This approach produced artworks that exhibit both the beauty of natural randomness and the coherence of human artistic vision, creating complex visual experiences that continue to captivate viewers decades after their creation. Contemporary digital artists use computer algorithms to generate random starting points for creative exploration, allowing entropy-driven processes to suggest new possibilities while human aesthetic sensibilities guide selection and refinement of promising results into finished artworks that blend computational randomness with intentional creative choices. The balance between structure and chaos appears crucial for maintaining creative vitality, while producing art that communicates effectively with audiences who seek both novelty and familiarity in aesthetic experiences. Too much structure creates predictability that lacks creative surprise, while excessive randomness produces confusion that prevents meaningful artistic communication, suggesting that optimal creativity operates within intermediate zones where entropy provides sufficient variation to generate fresh possibilities without overwhelming organizing principles that enable coherent artistic expression. This principle extends beyond individual artistic works to encompass creative careers and cultural movements that maintain long-term vitality through cycles of exploration and consolidation, innovation and tradition, experimentation and refinement. Understanding creativity as entropy management provides valuable insights for anyone seeking to enhance their innovative potential while producing meaningful work that balances originality with accessibility, surprise with coherence, and personal expression with universal appeal. Embracing uncertainty as creative fuel requires developing comfort with incomplete control over artistic outcomes while maintaining confidence in one's ability to recognize and develop promising creative directions when they emerge from the interplay between intention and chance that characterizes all profound artistic achievement. What profound psychological transformation occurs when we truly understand that impermanence isn't a cruel cosmic joke, but an inevitable consequence of the same statistical principles that enable stars to shine, flowers to bloom, and consciousness to emerge from molecular complexity. Embracing entropy's universal operation brings extraordinary philosophical relief by revealing that loss, change, and eventual dissolution represent natural features of existence, rather than arbitrary punishments or personal failures that we somehow deserve or could have prevented through different choices or greater effort. This thermodynamic perspective transforms our relationship with suffering from futile resistance against immutable laws toward graceful acceptance of temporary beauty within an evolving cosmos, where nothing remains static but everything contributes to the magnificent dance of energy dispersal and pattern formation that characterizes reality at all scales. When we recognize that our own bodies, relationships, achievements, and cherished possessions must eventually succumb to entropy's gentle but relentless influence, we can release ourselves from the exhausting struggle to make permanent what nature designed to be transient, finding peace in appreciating present moments rather than desperately clinging to past configurations, or anxiously attempting to control future outcomes beyond our influence. Understanding entropy reveals why fighting impermanence creates such profound psychological distress by placing us in opposition to fundamental forces that operate with mathematical certainty across the entire universe, making our resistance both futile and unnecessarily painful. The Buddhist concept of suffering arising from attachment gains scientific validation through thermodynamic principles that demonstrate the impossibility of maintaining any organized state indefinitely, without constant energy input that must ultimately cease when available resources become exhausted or environmental conditions change beyond sustainable limits. Accepting this reality doesn't require pessimism or despair, but rather opens opportunities for appreciating the extraordinary beauty that emerges precisely because it cannot last forever, like sunrise colours that captivate us partially because we know they will fade within minutes, or autumn leaves whose brilliant hues become precious through their brief duration. Before winter's arrival transforms the landscape once again, the knowledge that entropy governs all physical processes provides comfort by revealing that challenges we face in maintaining health, relationships, careers, and creative projects reflect universal principles rather than personal inadequacies or cosmic unfairness, targeting us specifically for difficulty and loss. Aging bodies experience entropy through cellular damage accumulation, protein misfolding, and DNA replication errors that gradually reduce physiological function despite our best efforts to maintain vitality through exercise, nutrition, and medical intervention. Recognizing these changes as natural consequences of thermodynamic laws rather than personal failures can reduce anxiety about growing older, while encouraging realistic approaches to health maintenance that work with biological entropy rather than against it through acceptance of limitations combined with gentle efforts to preserve function and quality of life within reasonable boundaries. Similarly, understanding that all human institutions and social structures must eventually transform or dissolve through entropy-driven processes can reduce distress about political upheaval, economic instability, and cultural change by revealing these dynamics as expressions of universal principles that have operated throughout history rather than unprecedented disasters threatening civilization's foundation. The beauty of temporary patterns becomes more visible when we appreciate their emergence from the same entropic processes that will eventually dissolve them, creating poignant awareness of precious moments that deserve full attention precisely because they cannot be preserved indefinitely. Snowflakes display exquisite crystalline symmetry during their brief existence before melting into formless water droplets, yet their transient nature enhances rather than diminishes their aesthetic appeal by emphasizing the remarkable coordination of physical forces required to create such delicate complexity under specific atmospheric conditions that rarely align perfectly. Human lives follow similar patterns, developing unique personalities, relationships, and contributions that enrich the world temporarily before individual entropy increases beyond the point where biological organization can be maintained. Yet this limitation makes each life more precious rather than less meaningful because conscious experience represents an extraordinary statistical victory over randomness that deserves celebration rather than lamentation. Thermodynamic knowledge can reduce anxiety about uncertainty and change by revealing these experiences as fundamental features of existence rather than abnormal disruptions requiring elimination or control, encouraging adaptive responses that flow with natural processes rather than exhaust ourselves through futile attempts to impose permanence upon inherently dynamic systems. Finding comfort in universal principles involves recognizing our participation in cosmic evolution that connects our personal experiences to stellar nucleosynthesis, galactic dynamics, and the gradual approach toward maximum entropy that gives meaning to temporary complexity by providing the thermodynamic context within which beauty, consciousness, and love can emerge as precious islands of organized pattern within the vast ocean of increasing disorder that defines our universe's journey through time toward ultimate equilibrium and peaceful stagnance. What essential life lessons emerge when we recognize entropy as a profound teacher whose curriculum includes the fundamental principles governing effort, maintenance, relationship preservation, and the delicate art of creating lasting value in a universe that naturally tends toward dissolution? Understanding thermodynamic laws transforms our approach to personal goals, professional projects, and meaningful pursuits by revealing why sustained achievement requires continuous energy investment rather than one-time efforts that we might naively expect to produce permanent results without ongoing attention and renewal. This perspective illuminates why successful gardeners know that beautiful landscapes demand regular watering, pruning, fertilizing, and pest management rather than initial planting, followed by benign neglect, and why thriving businesses require constant adaptation, customer service, innovation, and market responsiveness rather than static business models that worked effectively in past conditions. Entropy teaches that preservation demands vigilance because organized systems naturally degrade through thermal fluctuation, chemical weathering, competitive pressure, and countless other forces that slowly but inevitably erode structure, function, and coherence unless counteracted by deliberate intervention that supplies fresh energy and corrective action. This principle applies equally to maintaining physical fitness, preserving friendships, sustaining creative skills, and keeping homes clean and functional, revealing why periodic neglect leads predictably to deterioration, while consistent small efforts can maintain desirable states with surprising efficiency compared to major restoration projects required after entropy accumulates beyond manageable levels. Learning to work with natural tendencies rather than against them represents perhaps entropy's most practical teaching, suggesting strategies that harness statistical preferences for energy dispersal rather than fighting futilely against thermodynamic inevitability through approaches doomed to fail regardless of determination or resources invested. Smart refrigeration systems maintain cool temperatures by removing heat rather than trying to stop thermal motion directly, while effective communication strategies account for natural information degradation by building redundancy, confirmation mechanisms, and error correction into important messages, rather than assuming perfect transmission through single channels. Understanding these principles improves decision-making by helping us distinguish between achievable goals that work with entropy and impossible objectives that require violating fundamental physical laws, enabling more realistic planning that accounts for maintenance costs, degradation, rates, and renewal requirements when evaluating potential projects or commitments. Entropy reveals why procrastination becomes increasingly expensive over time as small problems compound into major difficulties that demand disproportionate resources to resolve, encouraging prompt attention to emerging issues while they remain manageable rather than waiting until entropy accumulates beyond easy correction. This insight applies to health maintenance, where early intervention prevents serious medical conditions, relationship repair, where addressing minor conflicts prevents major breakdowns, and financial planning, where regular saving prevents crisis situations that require dramatic lifestyle changes to resolve. The teacher entropy also demonstrates why sustainable systems must incorporate regeneration mechanisms that continuously refresh their components rather than depending on perfect preservation of original elements, explaining why healthy ecosystems cycle nutrients through death and decomposition processes that enable new growth, why successful organizations regularly recruit fresh talent while developing existing personnel, and why vibrant communities balance preservation of valuable traditions with openness to beneficial innovations. Appreciating transient beauty becomes a crucial skill when we understand that all aesthetic experiences involve temporary arrangements of matter and energy that will inevitably transform into different configurations, encouraging mindful attention to present moments rather than desperate attempts to freeze experiences that derive their poignancy precisely from their ephemeral nature. Cherry blossoms captivate observers partially because their brief blooming period creates urgency to witness beauty that will soon disappear, while sunsets gain emotional power through their daily cycle of appearance and dissolution that reminds viewers of time's passage and existence's precious fragility. This perspective encourages photography, journaling, and mindful observation as ways of honoring beautiful moments while accepting their temporary nature, rather than demanding permanent preservation that violates thermodynamic reality. Entropy teaching extends to career development by revealing why professional growth requires continuous learning, skill updates, and adaptive responses to changing market conditions, rather than believing that initial education provides permanent qualification for static positions in evolving industries. The most successful professionals understand that their knowledge and abilities will become obsolete without regular renewal, much like biological cells that must continuously synthesize new proteins to replace damaged components and maintain cellular function against entropy's degrading influence. This wisdom suggests viewing careers as dynamic systems requiring ongoing energy investment rather than fixed achievements that provide permanent security independent of external change and internal adaptation. Ultimately, entropy serves as a wise counselor that teaches realistic expectations about effort requirements while revealing the profound satisfaction available through skillful engagement with natural processes that transform challenge into opportunity and limitation into creative constraint that enhances, rather than diminishes, human potential for meaningful achievement within the beautiful context of universal change. What profound sense of cosmic belonging emerges when we finally grasp that entropy represents nothing more mysterious than probability theory, operating with mathematical precision across systems containing astronomical numbers of particles, transforming the seemingly arbitrary direction of time into an inevitable consequence of statistical mechanics applied to realistic physical conditions. Throughout our gentle exploration, we have discovered that the real reason behind entropy's relentless increase lies not in mysterious forces or cosmic conspiracies, but in the simple mathematical fact that when trillions upon trillions of molecules interact through random collisions and thermal motion, certain macroscopic arrangements become so overwhelmingly probable that alternatives essentially vanish from practical possibility, making mixed states inevitable while organized configurations become virtually impossible within any reasonable time frame. The universe contains no hidden preference for disorder over organization, no malevolent tendency toward destruction rather than creation, but simply follows mathematical laws that favor arrangements achievable through vastly more microscopic pathways than the special configurations we associate with reduced entropy and increased organization. Information loss emerges as the true driving force behind time's arrow, creating irreversible changes not through violations of fundamental physics, but through statistical scrambling of organizational details that become distributed among countless molecular positions and velocities in ways that cannot be practically unscrambled through random processes alone. When we crack eggs or burn paper or watch perfume disperse throughout rooms, we witness information about initial configurations becoming irretrievably scattered throughout microscopic degrees of freedom that preserve no memory of their historical origins, making reversal impossible because the universe has forgotten the specific arrangements that once existed while retaining only averaged properties like temperature and pressure that provide insufficient detail to guide reconstruction processes. This perspective reveals existence as an extraordinary statistical achievement where conscious observers have emerged temporarily from molecular chaos through energy-driven processes that create local complexity while contributing to universal entropy increase through metabolic heat generation and waste production that accelerates overall disorder. The deep connection between entropy, probability, and existence illuminates our privileged position within cosmic history as witnesses to a remarkable epoch when energy gradients remain sufficient to power stellar fusion, biological evolution, and conscious awareness, while the universe gradually approaches thermal equilibrium through processes that will eventually eliminate the temperature differences and chemical potentials that currently enable complex phenomena. We live during a brief window when matter can organize itself into patterns capable of contemplating their own nature, while participating in the grand thermodynamic journey toward maximum entropy that gives meaning to temporary achievements by providing the statistical context within which beauty, consciousness, and love represent precious victories over randomness. Finding gratitude for this moment of organized complexity transforms our understanding from anxiety about inevitable dissolution toward appreciation for extraordinary circumstances that enable experience, learning, creativity, and connection within systems that follow universal principles connecting microscopic randomness to macroscopic beauty through purely mathematical relationships. The steam rising from your coffee tomorrow morning will offer another opportunity to witness entropy in gentle action, as thermal energy disperses from concentrated sources toward uniform distribution while providing warmth and comfort that exemplify how energy flows can create pleasant experiences during their inevitable journey toward equilibrium. Every breath you take participates in atmospheric mixing processes that distribute oxygen molecules throughout your lungs, while removing carbon dioxide through diffusion gradients that follow the same statistical principles governing galactic evolution and stellar dynamics across vast scales of space and time. These daily encounters with thermodynamic processes provide ongoing reminders of our participation in cosmic patterns that connect personal experiences to universal principles through mechanisms so fundamental that they operate identically, whether we examine molecular collisions in biological systems or energy transfer in distant supernovae explosions. The peaceful certainty that some things in the universe are beautifully inevitable brings profound comfort by revealing entropy not as enemy or obstacle, but as gentle guide that creates the temporal structure enabling memory formation, relationship development, artistic creation, and all forms of meaningful achievement that require directional flow through time rather than eternal stasis in perfect equilibrium. Understanding entropy as probability in action encourages acceptance of change while inspiring appreciation for stability, promotes realistic expectations about effort, requirements while revealing opportunities for skillful engagement with natural processes, and transforms anxiety about uncertainty into wonder at the mathematical elegance underlying apparent chaos. As you drift towards sleep tonight, consider how entropy operates through your cooling body temperature, your slowing brain waves, and your gradual release from conscious control over thoughts and sensations, creating peaceful transitions that mirror the universal tendency toward equilibrium, while enabling restorative processes that will refresh your capacity for tomorrow's experiences with continuing mystery and beauty within our extraordinary universe where statistical laws create space for consciousness to emerge, flourish, and contemplate the magnificent improbability of its own existence.